Muy buenos días a todos, muchas gracias por su asistencia. Bienvenidos a la Facultad de Ciencias Físicas, a otra de las charlas que realizamos de divulgación científica de la Real Sociedad Española de Física, en colaboración con la Fundación Ramón Areces y dentro también del ciclo de Hablemos de Física de esta facultad. Hoy tenemos la suerte de contar como conferenciante con el profesor Stevens. So welcome to Faculty of Physics and thank you very much for coming. ¿Sí? Es un placer, como digo, poder contar con este conferenciante y también antes de empezar la conferencia me gustaría presentar a quienes están en la mesa con nosotros. A mi derecha, lo conocemos todos, el presidente de la Real Sociedad Española de Física, José Adolfo de Azcárraga, y a la izquierda, don José María Medina, en representación de la Fundación Ramón Areces, a quien paso la palabra. Gracias.
Muchas gracias. Mi nombre, como ha dicho la decana, es José María Medina y soy el consejero científico de la Fundación Ramón Areces, desde donde le doy la bienvenida a esta conferencia. La Fundación Ramón Areces, como probablemente ustedes todos conocen, fue establecida hace ahora 42 años por Ramón Areces, que después de crear los grandes almacenes del Corte Inglés, al final de su vida decidió ceder su fortuna para la fundación de la que llevaría su nombre como Fundación Ramón Areces. Una fundación que desde su principio tiene como objetivo fundamental la promoción de la ciencia en España. Para ello llevamos a cabo muchas iniciativas, de las que yo destacaría tres principalmente. La primera de ellas es la promoción directa de la ciencia a través de financiación de proyectos de investigación en todas las áreas en las que nos corresponde a nosotros de la vida y de la materia. En segundo lugar, para ayudar a nuestros estudiantes de doctorado que puedan hacer unas estancias postdoctorales en el extranjero, todos los años se convoca unas becas postdoctorales para estancias en el extranjero en los temas más frecuentes, que son el de biomedicina, física y matemáticas, y preservación química y preservación de la biosfera. Con estas estancias, con estas becas, lo que promovemos son las primeras estancias postdoctorales en el extranjero. Y en tercer lugar, intentamos ayudar a la organización de eventos como este. Hoy estamos dentro del ciclo de esta facultad de Hablemos de Física, que está, digamos, promocionada por la Sociedad Española de Física y en este caso también por la Fundación Ramón Areces. Repito el agradecimiento por vuestra asistencia a este acto y cedo el micrófono a la excelentísima señora decana.
Muchas gracias. So, Professor Azcárraga, would you please introduce our guest?
Good morning to everybody. We are very happy having here Professor Jueves, who is the director of the Max Planck Institute for Meteorology and Atmospheric Science of Hamburg. He is also professor at the University of Hamburg. Before, he was professor of the University of California in Los Angeles and in other places. I'll be brief introducing him, because what it is important is what he has to say, but I'll say that his area of research is both theoretical and experimental, and he is devoted to modeling the structure of clouds and the effects of aerosols. This is important in the overall energy balance of the energy, and which is in turn essential in the hydrological cycle of the Earth, and ultimately in the problem of climate change. He has received many awards, and I will mention just from the American Meteorological Society, the National Center for Atmospheric Research, and the Humboldt Society. And having said that, I will stop here and have Professor Stevens say whatever he has to say, which I'm certain is going to be very interesting.
So, thank you very much. I wanted to thank the faculty and the Society and the Foundation for making it possible for me to share some of my thoughts with you today. Is the sound okay? Can you hear me okay? Speak louder? Okay. So what I might be able to do is move this higher. I don't know, does that make much of a difference? But I can keep, if you don't hear me, I'll try to speak up. I thought today I'm not going to talk so much about my own research because I had the idea that I'm coming to a physics faculty and that there would be students of physics, and what I was hoping was that I could convince you today that climate change is fairly simple and our understanding of it is fairly simple, and it's based on physical ideas rather than complicated models. We once in a while use the complicated models to see if our thinking is off course, but the main ideas that underpin our understanding of climate change are actually quite simple. So I would try to explain those to you today in the next 45 minutes or 50 minutes. Maybe I'll try to make 3 points. In the one I will really talk about how greenhouse gas warming works and why it increases surface temperature. The next part I will talk about is what that implies for changes in the hydrological cycle, why we think patterns of rain will change in a certain way. And at the end I'll talk a little bit about maybe some surprises, some exciting things. I have the presentation on this computer, and so there's some videos which are sort of, I kind of think they're kind of old-fashioned climate model videos. I have a video which is more state-of-the-art, so at the end, if you want to see really where the frontier is in modeling, I can show you that at the end, but then I would have to hook up my computer. Anyway, so let's begin about these simple principles underpinning climate change. So if I can scroll there. This is, just as a caveat, yesterday I was at the other university, the Autonomous University, and I spoke about the role of clouds. So some of the slides, I think a couple of people were there yesterday. Some of the slides are the same, but I won't talk that much about clouds in the presentation today. But this was a slide I showed yesterday, and it shows really the two views that you need to take of the Earth to understand climate change. One is the view of how it gets its energy from the sun, and that's what we're seeing here. We're seeing from space the Earth illuminated by sunlight, and it's reflecting some of that sunlight back, mostly by clouds. So the ocean is dark blue, the clouds are white, and that determines the energy balance. We get about 340 watts per square meter on average from the sun over the Earth. And the clouds and ice sheets and the bright land surfaces reflect about 100 watts of that. So the net insolation, the net amount of energy that we get from the sun is about 240 watts per square meter. So if we keep accumulating 240 watts or joules per second of energy over time, of course you will heat up, and that's what the planet does, it heats up. And as it warms up, it radiates its own energy away at some temperature. And it will keep warming until it radiates as much energy as it gets. And that's what we see in this satellite picture here. So this is how the Earth would look like, well, it's how it does look like from space. It's a satellite image. And it shows you the Earth as if you would be in space looking at it through sort of infrared glasses. So if you look in the thermal infrared, so here we get the energy in the visible, 550 nanometers. That's called the mid-visible part of the spectrum. And that's because the sun is hot. The Earth isn't nearly as hot as the sun, so it radiates its energy at a longer wavelength, about 20 times longer, about 10 microns most of the energy is, but this is at 6 microns. And so if you're in space and you're looking at the Earth, you see a picture that looks like this. The interesting thing about this picture here, this one here you can kind of, does anyone recognize anything? Do you imagine where we're at here when we're looking at the Earth? You know, what part of the Earth we're looking at? Anyone want to guess? So if you look up here, you can see the west coast of North America here. So we're here looking over the sort of South Pacific Ocean. That's why it's mostly blue. But the point is you can look, if you look really closely up here, you'll see a little bit of land, but you can recognize the surface of the Earth. This one, does anybody know, could you recognize anywhere where we're at? I mean, there you have no idea. So when you look at the infrared, what do you see? You see the Earth, it looks kind of like a gas that's swirling around. It looks more like a gas giant planet. And that's because we can't see to the surface when we look in the infrared. When we're looking into the infrared, we're just seeing into the atmosphere, and it's a swirling, we're mostly seeing water vapor swirling around. These are very deep, high clouds, which are cold, so they emit very little energy. And this is seeing very deep into the atmosphere, so it's black. So we're seeing very deep where the atmosphere is warm. But here we're seeing how the Earth radiates its energy away. And the whole way to understanding climate change is really by understanding what greenhouse gases do to this picture. So the fact that we don't see to the surface is because the atmosphere is opaque. And it's opaque because it's a greenhouse atmosphere. That means that in the infrared, it's not transparent. It's the opposite. It's opaque, and you only see to a certain depth. And depending on how much greenhouse effect there is, you see very deep into the atmosphere where it's black, so that's you see a lot of energy, or you don't see very deep. So which greenhouse gas do you think we're mostly seeing in that picture? So I said you don't see very deep into the atmosphere because there's a greenhouse gas there. Which one do you suppose that is? What's the most important greenhouse gas? The most absorbing gas in the infrared. So it's water vapor. So mostly what we're seeing is water vapor, and this is the dry subtropics. That's where the atmosphere is fairly transparent, here and here. And this is the humid tropics. This is the convergence zone. This ends up being South America during the daytime. And what you see is very deep convection, making the atmosphere very opaque. This is Africa. And again, you see deep convection making the atmospheric opaque. So these are areas where it's fairly humid. These are the storms that we have, the winter storms, or the extratropical storms that wrap up water vapor. You can see a sort of cyclone there. But you see this is a picture of water vapor, and that's radiating away. So if we understand that, what do we know about, how can we think about climate change? And here I want you to keep this picture in mind of looking at the atmosphere as a greenhouse atmosphere, that you're not seeing to the surface, but you're seeing energy radiated away. And the simplest way to think about a greenhouse effect, and the simple principle is I'm going to illustrate with this figure. And this is a figure which shows, you can think of amount on this side. So it could be temperature in the case of this red curve, or it could be humidity in the case of the blue curve. And this is pressure or height. So as you go up here, you go higher in the atmosphere. And as you go here, you increase the amount of something. So the red curve shows the typical temperature structure in the lower 15 or 20 kilometers of the atmosphere, which means temperature decreases with height on average until you get to the tropopause, which is about 100 Kelvin or 100 degrees Celsius colder than the surface. And then it increases again in the stratosphere. So this is a typical temperature profile for the atmosphere. And because the temperature is cooling, the saturation vapor pressure, the amount of water that you can maintain without it becoming condensed, is a function of temperature, and that decreases along this dashed line. And the actual humidity of the atmosphere more or less follows this curve, and I'll show you data to that effect later. But this is the humidity profile. So you see there's lots of moisture in the surface where it's warm, and then as you go higher up, you can't maintain vapor in water in the vapor form because it condenses out as rain, and so that decreases with height. The scale height of this is about 2 kilometers. So what happens is energy comes into the surface, the sunlight goes more or less through the atmosphere, which is transparent. It accumulates at the surface, it warms the surface, and then the Earth radiates energy away. So if you look here, when you look in this picture, what you're seeing is to about an effective height. You're seeing not all the way to the surface, but on average, a certain depth of the atmosphere. And this would be the sort of effective radiative depth that you see into here. So it turns out the temperature here has to be at a certain value so that you lose as much energy as you get. So if we said we got in the net, how much energy do we get from the sun? Does anybody remember that number I said? It was 240 watts per square meter. So then you can figure out if you're radiating as a black body, sigma T to the 4th, how warm do you have to be to radiate that much energy? And the question is, how warm do you have to be, but where do you have to have that warmth? Because the effective radiation is coming from a height which is determined by the optical depth of the atmosphere. So if the optical depth of the atmosphere is very thin, then the radiation comes from deep in the atmosphere. If it's very thick, then the radiation comes from very high in the atmosphere. But at that effective depth where the radiation is coming from, the temperature has to be about 255 Kelvin. So in the present atmosphere, the optical thickness, how greenhousey it is, sets the radiative depth, say, about here, and this temperature would be about 255 Kelvin. So what happens when you increase the amount of greenhouse gases in the atmosphere? What do? You make it more opaque, right? The atmosphere becomes sort of soupier, thicker. If you're in outer space and you increase the greenhouse gas in the atmosphere and you look at the atmosphere, you don't see as far into the atmosphere. So instead of seeing all the way down to here, you see less deep, so you only see to here. But what happens if now you're irradiating, before you're irradiating here enough energy to balance the sunlight, now if the atmosphere is thicker, you're effectively radiating heat from this level here. But you see this level, because the atmosphere is stratified, this level is colder than this level. So with more greenhouse gases, what you find is that you don't radiate enough energy away for the system to balance the incoming energy. So what do you have to do? So the atmosphere is now optically thicker. You radiate from a higher level where there's less temperature. You don't radiate enough energy. So the simplest thing for the planet to do is just to warm up. And this is the basics of the greenhouse effect, and it's very important that you think about it from not looking up, but from being in space looking down and imagining how far deep into the atmosphere that you can see. And then depending on how deep you can see into the atmosphere, that determines the temperature there. And then through this change in temperature with height, which we think shouldn't change very much for reasons I can explain later, then you can infer that the temperature at the surface would be much warmer if you have an optically thicker atmosphere. So the greenhouse effect is that simple. You can calculate this with simple models, and you can quantify how much you expect the temperature to increase if you increase the optical depth of the atmosphere. Now there's an important aspect to this, and that is, whoops, that's this guy here. So this is, does anybody know this equation? Has anyone seen this? This is the most important equation in climate physics. And it's a direct consequence of the second law of thermodynamics. And it's called the Clausius-Clapeyron equation. So I don't think there's a more important equation in climate physics. Almost everything we know about the climate system, some way or another, seems to have something to do with this equation here. And the variables here is, this is the saturation vapor pressure, and this is temperature, and this is a thermodynamic constant that's roughly related to temperature. So what it says is that when you look at the Clausius-Clapeyron, it says that the temperature controls the saturation vapor pressure, the amount of humidity you can maintain in the atmosphere. Excuse me. So why is that important? So it's important because what's the most important greenhouse gas? Water vapor. So if you put in more CO2, you make the atmosphere more optically thick, you warm it. But if you warm it, then you would have more water vapor, which increases the optical thickness of the atmosphere, which causes it to warm more. And if you look at the atmosphere, what you find is that this is data now from SONs that go up all around the world every day over many, many years. And this is temperature, and this is this value of the vapor pressure. And this is the theoretical curve that you would get if you were saturated. So if you're saturated at a warm temperature, you have a lot of vapor pressure because you can maintain a lot of vapor at warm temperatures. At a cold temperature, the saturation vapor pressure is much smaller. This is a logarithmic scale here. This is linear. And so what you see is that there's a very strong increase in the saturation vapor pressure with temperature, theoretically. And if you measure at different heights, that's what these different colors are. If you measure at different heights, low in the atmosphere where it's warm, what you find is you follow very closely this black line. And then you follow here. So the point is, if you warm the atmosphere, what you would expect is that the ratio of the actual vapor pressure to the saturation vapor pressure, the ratio of this point here to the saturation, the difference between these two, that's the relative humidity. What you expect is in a warmer atmosphere, because this is such a controlling factor on the humidity of the atmosphere, you would expect that to be more or less constant. You would expect that the saturation vapor pressure increases with temperature, and that the actual vapor pressure follows the saturation vapor pressure. So one of the key ideas in climate change research is that the relative humidity of the atmosphere stays more or less constant. So if you increase the temperature by 10 degrees, you keep the relative humidity constant, which means you increase the absolute humidity almost by a factor of 2. So for a 10 Kelvin increase in temperature, you would expect the absolute humidity, the total amount of water molecules in the air, would increase by about a factor of 2 in order to keep the relative humidity the same, because the atmosphere is much better at regulating its relative humidity than it is its absolute humidity. Why would that be? Why would the atmosphere care more about regulating its relative humidity than the absolute humidity? So how do you get rid of water in the atmosphere? So water keeps going to the atmosphere, it evaporates, right? We have big oceans, so water goes into the atmosphere. So how do you get rid of it? So it keeps putting water in the atmosphere, it keeps putting it in until what happens? It becomes saturated, it rains out. So the valve, the thing that controls the amount of water vapor is really this condensation, precipitation. But to condense, you have to become saturated. So the saturation curve is really important for how much water vapor you have in the atmosphere. So the idea, a big idea in climate is that the relative humidity stays about constant. About means, you know, maybe the relative humidity is 50%, maybe it's 60%. But that's much less of a change than the factor of 2 that you would see in the absolute humidity if you increase the temperature 10 degrees. So an example of this, is shown here, and these are calculations that were done 50 years ago, where you look at the atmosphere as a one-dimensional system where you have energy flowing in and then you have energy flowing out, and you try to find a balance between those two, something that's called radiative convective equilibrium. And here, when people first began doing that, what they did was they said, what should we do with the humidity in this calculation? If we have energy flowing in and energy flowing out, the humidity is an important greenhouse gas. What happens to the humidity as the temperature increases? And so they looked at data, and this is an example of data. So this is summer and this is winter over the northern hemisphere. So this is equator and this is the northern hemisphere. And they had just begun to get a good picture of how water vapor is distributed through the atmosphere. And the main point of this figure was to show that if this is the relative humidity, look, this line, it's 60%. It kind of goes up and then it goes down and then it goes up again. And if you look here, this is 60%. It kind of goes up, it kind of goes down, and it goes up again. The temperature difference between summer and winter at 70 degrees of latitude is huge. So if you go to 3 kilometers, here, if you go to 3 kilometers and 70 degrees, you're at, say, 57% relative humidity. And if we do it up here, maybe you're at 59% or 60% relative humidity. But the temperature change between summer and winter is large. It might be 10 or 15 degrees. So if absolute humidity had been constant, the relative humidity would change by a huge amount. So the point of this figure is that, sure enough, you would expect relative humidity to be relatively independent of temperature, and these two curves look fairly similar. So we will take this as a foundation. We'll say the relative humidity is fairly constant. And then we can calculate in a one-dimensional model, a simple model where energy comes in from sunlight, it goes to the surface, it's redistributed through the atmosphere through convection, and the atmosphere then loses the energy to space, like we saw in that picture. And what people did when they calculated that is they said, well, if you double amount of CO2 with those assumptions, then you will find that the temperature change at the surface increases by somewhere between, say, 1.3 and 2.3 Kelvin. So this is a number that people call the climate sensitivity, how much the surface temperature would change if you increase the amount of CO2 by a factor of 2. And they found it was this amount. And they found that about half of that change came directly from increasing the CO2, and the other half of that change came from the water vapor increase that accompanies that. So if you didn't allow the relative humidity to increase, you would have only expected about half of the temperature change that you see here. So a long time ago, they had this estimate of what we call the climate sensitivity, and they realized when they made this estimate that they had to correct for some things that the model left out. So it's a very simple model based on the principles I talked about, but they had to correct that model because it didn't include the fact that surface ice would go away. So if you have a warmer climate, you expect for sure to have less snow, and snow reflects sunlight, so you'll absorb more sunlight. And so they tried to correct for that as best as they can. You can look at how ice varies with temperature and seasonal cycles. You can make simple models of that. And instead of these black points, what you found then is that the planet becomes a bit more sensitive. So you would be over here somewhere. The planet becomes a bit more sensitive to increasing CO2, not only because increasing CO2 makes the planet the atmosphere optically thicker, more water vapor makes it optically thicker, but now you have less ice, so you absorb more sunlight. So you get over here. What was left out a lot of these calculations was how clouds would change. And what they realized at that time was that clouds make things a bit more complicated, because if you had more clouds, maybe the planet would cool. If you had less clouds, maybe the planet would warm. So then they sort of just put their thumb in the air and they said, well, based on some primitive models that they had at that time which incorporated the cloud effects, they said, let's expand this range here to be a somewhat larger range. And so this is how people reasoned their way to this idea that if you double CO2, you would change the surface temperature by somewhere between 1.5 and 4.5 Kelvin. So you start with a physical model, you calculate the physical model, you correct it for the things that leave out, and then you sort of inflate the uncertainty for the things that you don't understand. But they're all very simple calculations. Now you can say, well, the Earth isn't one-dimensional. You have energy coming into the equator, it's transported to the poles, it's lost at the poles, so then you can say, well, maybe we're really far off with these calculations because it was such a simple model. So maybe we can try to see, is the Earth different if we allow for these other things to happen? If we allow for the energy to be accumulated at the equator, we try to calculate how it's transported to the poles, and then we reproduce the calculations where we resolve a bit the spatial flows of energy. So already back in the 70s, they had developed some of these first circulation models where they could do the energy transport from the equator to the pole. And they're quite primitive, but they look sort of like this. Instead of just a simple one-dimensional model, they would make models that look more or less like this by the 1970s or so. And what you can see in the model in the white, these are supposed to be the clouds. They're kind of pasted into the models. Those models don't do the clouds, represent the clouds very well. But you see here these sort of swirling motions here that move from west to east. So in the westerlies here, you see them down here. These are storm systems that would develop in the westerlies. So winter storms, as you know them here, and they would bring moisture and heat from the tropics into the extratropics. So the accumulation of energy you get from the sunlight at the equatorial latitudes is transported to the poles, it's radiated to space. So in these models, you tried to address for one of the weaknesses of these simple one-dimensional models. But what you found was that when you did that, you didn't really change this picture that I showed before. These assumptions that you made in the one-dimensional model that the relative humidity was more or less constant are relaxed in this model. You don't keep the relative humidity constant. You try to calculate what the relative humidity is by transporting water vapor, condensing it, letting it fall out. But what you find is that if you try to do that, the assumption wasn't bad either. So you had the data that said it's not a bad assumption. Now you try to calculate things with models, you say it's not so bad either. The models also showed that clouds lead to lots of uncertainty. They still do. So you don't really believe the model in terms of what it's doing about clouds, but how it's moving water vapor around the system makes you believe your simple assumptions about water vapor. So these models had problems with clouds, but the basic tenets that we talked about before were still okay. Now, if you fast forward to, I would say the present day, if you look at when people do these big international reports for climate change, they actually don't use models which are a whole lot different than these ones. Structurally, they're very similar. They like to talk about them as being very sophisticated, but the clouds are still pretty crude in these models. So here I can play this one. So you can see, now this is model, it's a bigger picture. It has more color, it's more modern. But the basic principles through which this sort of model works aren't that different than the one that the other model was. It has just a lot more spatial resolution. So it can represent the quasi-two-dimensional fluid dynamics that transport heat from the equator to the pole a lot better. So it allows you to look at this humidity assumption that we made a lot more closely. It represents how the humidity is transported much better. But in the end, the answer doesn't differ very much from these types of models and the ones we saw before. There's lots of weaknesses of these types of models. They're still fairly primitive because they have to, in a way, I was saying this yesterday, they kind of paste on the clouds. They represent the circulation, but the clouds are kind of pasted on. You say, well, when air goes up and it gets cold, then we'll make a cloud or not a cloud, but the clouds aren't really naturally represented. And the way they form rain, there's all sorts of issues, but the heat transport that goes to the pole is sort of well represented. So we say, okay, well, based on that, we kind of have confidence in these very simple ideas that we started out with a long time ago. So here, if you come back to the present day, I say this is the state of the start because we're entering a new era. That's what I can talk about at the end of climate modeling. And I think I call us the start of this new era. But if you look at this old era up until now, We had already in the 1970s these very early one-dimensional calculations. So this would be temperature that you get from doubling CO2. And so if you look here, these early calculations I showed before were like 1.5 to 2-ish in here. You correct for the surface albedo, the fact that ice goes away when it's warmer, and you get here. And then you say, well, let's inflate the uncertainty from this estimate to account for the fact that we don't know what clouds will do, and you get this famous 1.5 to 4.5 degree range in terms of how much warming you would have if you double CO2. So that's how we got here over a period of 30 or 40 years. And now you build all sorts of models that try to explore the assumptions that you made in here, and what you find is that the models, this is a histogram of the number of different models, how they've gone over time, and you more or less see you populate this same range. So the models haven't given you a real reason to think differently about the problem. It turns out when you look at this distribution, what you find is it's actually not too hard to make models which are over here, where you can make a model where the clouds change in a way that make the climate sensitivity very large. It's hard to make models over here. So here the models are kind of happy, but it turns out if you try to compare these models to measurements, it doesn't work very well. So I always say to have a high climate sensitivity, you can do that easily with a model. The models are happy, but the measurements aren't very happy. If you're over here, kind of over in this side of the range, you can find quite a few measurements which suggest that's not unreasonable. So a climate sensitivity of about 2 on the lower range. But it's really hard to make models that come over here. So there's this sort of sweet spot in here where both the models and the measurements seem to be happy. That's another reason why we think the climate sensitivity is here. We can imagine a way to construct the system where you have a climate sensitivity above 2. It's really hard to make a model with a climate sensitivity less than 2. And the reason comes back again to water vapor. Because to make a climate sensitivity really low, you have to make the atmosphere dry out. You have to reduce the amount of water vapor as you get to a warmer climate. So you can say, fine, let's imagine a process that makes the atmosphere become drier as the climate warms. So we did that with one of our models. We said, let's make it as dry artificially. We made something up because we wanted to make a model that wasn't very sensitive to CO2. Whoops. So the goal was to make a model that wasn't sensitive to CO2. We tried to do something over here. And the way you do that is you make the atmosphere dry out. But what happens when the atmosphere is dried out? What do you think, what else would you expect would happen if you dry out the atmosphere in the model? So if it's not very moist, what do you think goes away? Clouds. It's hard to have a really dry atmosphere and lots of clouds. So you have this tension in the model. The humidity is what's making it warmer. And to make it not get so warm, you have to dry it. But as soon as you do that too much, what happens is it's hard to keep the clouds in the model. And if your clouds go away, then you get more sunlight. So there's this sort of, so that's what I mean when I say it's hard to make models over here, because I'm not very good at this pointer. It's hard to make models over here because in doing that, you have to dry out the atmosphere. And if you dry out the atmosphere, you get rid of clouds. Okay, so I hope I convinced you that this idea that relative humidity is constant is a nice working point for thinking about the atmosphere. So just accept that for a while. Let's pretend that the humidity of the atmosphere is constant, and we'll pretend that happens because as we warm the climate system, the processes which regulate relative humidity, the circulation systems, don't change drastically. They might change a little bit, but they don't change in a way that really hugely affects the relative humidity. So here, just the remarks on this point. I just wanted to say that increasing the infrared opacity of the atmosphere, you expect it to increase the surface temperature. A large amount of the warming arises from changes in the absolute humidity that you get if you assume the relative humidity is constant. We've developed more comprehensive models to account for some of the assumptions, to relax the assumptions that we've made in these first 2 points. And what we find is that this relative humidity premise that we used in the simple models, you can interpret as a consequence of the fact that the circulation doesn't change a lot when the climate warms. Even though the circulation doesn't change a lot, you could say locally, if you just shift the storms a little bit north or south, that has a big influence on regional climate. So this doesn't really help us, these more complicated models, when we look at regional climate. And it doesn't really help us in terms of clouds. But here's this point I wanted to come to, is that based on this, let's look at what happens if the relative humidity is constant in terms of precipitation. And here it's good to do a thought experiment. So now we're going to switch to something else. We're going to say, okay, the planet's warming. I tried to explain a bit why. And now we're going to say, what happens to the water cycle when the planet warms? And one way to think about this is to go back to this 1D world that I imagined before, where everything is uniform. So you get a certain amount of sunlight that's coming in, and you're losing energy through the atmosphere. And so really the heat balance of this simple one-dimensional world is one where sunlight comes in, it goes through the atmosphere, it's transparent to visible light, the sunlight goes to the surface and warms the surface. The atmosphere loses infrared energy to space because it's optically thick. So what happens in this world if you're losing energy from the atmosphere, because it's a greenhouse atmosphere, and you're getting it at the surface? So you're cooling the atmosphere and you're warming the surface. So the atmosphere gets colder and colder, and then the surface gets warmer and warmer. So to find a balance, what will happen? You need to transport heat from the surface into the atmosphere. So the surface has to warm the atmosphere to balance the energy it loses. So a greenhouse atmosphere loses energy to space, and the energy gets put back in by these guys, clouds. So the clouds take water vapor from the surface, evaporation of water vapor from the surface cools the surface, it balances the accumulation of energy from the sun, but it condenses in the atmosphere, which warms the atmosphere. So this transport of enthalpy from the surface into the atmosphere is what balances the radiative deficit. So radiation is driving a system by cooling the atmosphere and the infrared, warming the surface, and convection is balancing that. And the convection has two parts, the rain and the evaporation. So here I was using German symbols, which I didn't change, but this V is Verdunstung, so this would be evaporation, and N would be Niederschlag, which would be precipitation. So this would be evaporation, precipitation. And so what you would expect in this homogeneous world is that the clouds are like little heat engines which take moisture from the surface, evaporate it, form rain, and then it rains everywhere. And you would expect, of course, in equilibrium that the evaporation has to balance the precipitation. So now you know what determines how much it rains. If you look at the Earth as a whole, how much does it rain? Anyone know? Global average rain? It's about 3 millimeters a day on average, which is about a meter per year, globally averaged, if you look at the planet as a whole. So 3 millimeters a day, about a meter per year of rain, roughly. Why? Why a meter a year of rain? Why can't it be 10 meters a year, or half a meter? But you kind of know the answer, right? What is the rain? Why does it rain? It rains because of the greenhouse effect. What's the greenhouse effect? The greenhouse effect is this idea that the atmosphere is losing energy to space. The atmosphere is cooling. So if you know how much the atmosphere is cooling, then you know how much heat you have to transfer from the surface into the atmosphere. So the amount of rain is really constrained by this heat balance. You know how much energy is being lost by the atmosphere, you know how much is accumulated by the surface, and the rain is what balances the whole system. So if the greenhouse effect increases, what do you expect for the rain? If you're cooling the atmosphere more, it will rain more. So it turns out that you can calculate that just by spectroscopy. You can say, well, if we increase the greenhouse effect, we'll increase the rate at which we cool the atmosphere, and that has to be balanced by rain. And what you calculate is that for every degree of warming, you'd expect the rain to increase by about 2%. So you get about 2 to 3% increase in the amount of rain per degree warming. But it's just simple radiative transfer spectroscopy physics in a 1D world. And it ends up working for a very much more complicated world, as best we can tell. But the issue I wanted to get at here is that we know the atmosphere has a circulation, so not every point is the same. And we know, for instance, Madrid doesn't get as much rain as Hamburg, and that's because of the atmospheric circulation. So what happens on the Earth when you have a circulation is you don't have a picture like this, you have a picture that looks more like this. That you have rainy regions and you have evaporative regions. So if you go over the trade wind regions of the ocean, you don't have a lot of rain, but you have a lot of evaporation. The V again is evaporation. And here in the rain belts in the tropics or in the mid-latitude storms, you have a lot more rain and a lot less evaporation, relatively speaking. And the thing that connects the two is circulation. So circulation then transports water from the evaporative regions, where you evaporate a lot, into the raining regions. So here locally you no longer have a balance between precipitation and evaporation. There's very little rain here, but there's lots of evaporation. And over here, there's lots of rain and less evaporation because the air is moist. And the circulation, that's what I've drawn here, the circulation transports moisture into the rainy regions and transports energy out of the rainy regions. So now if you look at this system, what you have is you have an imbalance here and an imbalance here. Now let's think about this. If the circulation, let's imagine a world where this circulation stayed constant, or the circulation didn't change very much, and we increase the temperature. What would happen if we increase the temperature and the circulation was more or less the same? So this circulation, what's it doing? What is it doing? It's transporting moisture, right? So if we're in a warmer world, the absolute humidity of the air is larger. So if the circulation is the same and the relative humidity is constant, this circulation is transporting more moisture, which means that the difference between the evaporation and the precipitation will be larger because that's balanced by the moisture transport. And the difference here between evaporation and transpiration will be larger. Do you follow that? This is in an evaporation part. That's where air is evaporating. This is a rainy part, so here the precipitation is more than the evaporation. And it's connected by a circulation. And if the circulation were to stay constant, then you would expect it to transport more moisture. So what does that mean from the point of view of the rain? It means that here, if this is transporting more moisture, that the difference between precipitation and evaporation will be larger here, and it will also be larger here, but at the opposite sign. So if at the same time, let me go back here, so you can look at this idea of the effect of the circulation, is that you see from the circulation here, you have rainy regions and dry regions, and I just tried to show this on the globe. That's what I was showing before. So the brown here is where the evaporation is much larger than the precipitation. So it's a positive number, evaporation minus precipitation. You have more evaporation in these, so we're up here. These are the trade winds in brown. And the green is where the precipitation is much larger than the evaporation. And that's the rain belts in the tropics or the stormy regions, so Hamburg's up here. So this is just a picture of the actual data from the Earth of how it looks like, that the rain isn't distributed uniformly, that there's circulations that capture this, and they transport moisture from these evaporative regions into the moisture regions. So and now if you make the world warmer, what you expect is, if my picture changes, is that we know from the atmosphere is that if you warm the place, you would expect that the amount of precipitation to increase, like I said before. So you're increasing the amount of precipitation. And we know the rate just from from spectroscopy. It should be about 3% per Kelvin. But from the second law of thermodynamics, this increase of humidity with temperature, if the humidity stays the same, that means you're increasing the amount of humidity by, it turns out that this is 6 degrees per Kelvin, or 6% per degree Celsius. So you have this imbalance. As you warm the planet, if you keep the relative humidity constant, you expect it to rain a little bit more, but you expect the circulations to much more efficiently carry moisture. So how do you balance that? The moisture, you know, the circulation wants to carry more moisture into the rainy region, but the energy budget doesn't want it to allow it to rain that much. So what the way you balance this system is you shrink the rainy regions. This is yeah. So you go there. So this would be the present day, and when you go warmer, then you expect a rainy region to yeah, well, I will skip through because it seems like didn't like those slides. So when you look at the perspective as a whole of rain versus evaporation, what you find is that you have this precipitation minus evaporation. You have rainy regions. This would be a distribution of this P minus E over the Earth. So you have rainy regions and you have dry regions. And in the present climate, the distribution might look like this. But in a future climate, what you expect is you warm the system to broaden this distribution. So this is all coming from this thinking of the relative humidity being constant. You would expect to have a broader distribution of P minus E. And this means, this is the basis for when climate scientists say, well, we expect things to be more extreme because of this imbalance between the transport properties of the air and the radiative properties of the air. And I think it's actually a very interesting thing of this P minus E, because I don't know if any of people followed this past year. There was these huge fires in the summer in California where I used to live. So they had these enormous fires, which just kind of, this is a neighborhood that was destroyed. And don't get me wrong, I'm not saying that this is due to climate change, but I'm just saying the fascinating thing about this year was that they had the enormous fires. But if you went back 6 months before that, they had enormous floods. So I don't remember if people remember a year ago, they had winter rains in California, and they were so large that the dams were bursting and they were evacuating people. And so here you see tremendous winter rains. It's also in Spain where you have this sort of Mediterranean climate where you get a lot of winter rains and summer dryness. So in a warmer world, if you have the same seasonal cycle, but everything's warmer, then just this simple physical reasoning leads you to think that in a warmer world that the rains will be rainier when they rain and the dry periods will be drier. And this is an example of how the seasonal cycle worked this year in California. The interesting thing was no one predicted this, even though they should have, because when you had these tremendous rains, you had this huge growth of biomass. And then you go into a warmer summer, but if it's a warmer and a drier summer, you can dry things out much quicker, which makes it very susceptible to fire. You actually see a little bit of this evidence in the paleo record if you look at charcoal. So as you come out of the Holocene and you come out of the last glacial maximum when it was fairly cold and you go to warmer and warmer temperatures, what you see is more charcoal deposits, which is a signal of increased biomass burning as part of the seasonal cycle. So if you go into the sort of Sahel region where you have big seasonal fires, or in the sort of south equatorial Africa where you have a wet and a dry season, and in the dry season things burn and the wet season things grow, what you see as temperature goes up is that the amount of burning seems to increase. So this is the underlying idea of why we think precipitation will increase, but also the extremes will increase with warming. So what I wanted to say here, and then I'm just to my last part, which is fairly short, is that ultimately climate science is not about complicated models. It's about physical reasoning through ideas, and the ideas end up being very simple because we can't really understand more than simple ideas anyway. And I tried to give a picture of some of those. And so that when you hear prognoses, the ones that we are most confident about are the ones that are really rooted in some physical argument. Because a physical argument has this wonderful property that it allows itself to be evaluated from many different perspectives. The last thing I wanted to talk about here is surprises. So one of the fun surprises, and I will go back to this 1D example here, is when we go back now taking these modern models, and we go back to solving very old problems, this one-dimensional problem. You have a certain amount of sunlight coming in, it goes to the surface, you transport it through convection to the atmosphere, and it rains. So if you take one of those models that I was showing before, and you look at this heat balance, which I just drew here, you have energy coming into the surface here, you're losing it through LR, the clouds are matching it. What you find is that this would be the globe as a whole. So right now it's not a rotating Earth, there's no continents, it's just getting energy everywhere the same, and it's losing energy. But what you find is that the precipitation tends to clump in places in these models. So you can say, well, you know, this is the size of like, you know, Africa. It's a huge area which is raining, and this is a huge, but you just get this random distribution of precipitation that clumps. What you find is if you change something in how the models form rain, is you can get very different pictures of how the rain is distributed. So this is now going to things that we don't know, which are sort of a bit more mysterious, is that here I just made slightly different assumptions about how I allow the model to form rain. And what you see is a completely, you know, if you look at these, the blue is rainy areas, you get a completely different distribution of rain in these different worlds. And what you find is that as you increase the temperature in these worlds, you go from a world that looks like this, where the rain is sort of homogeneously spread out, to more worlds that then go like this, and they go like this and like this. So this depends on some assumption in the model, but it also depends on the temperature. In a warmer world, we tend to go from a distribution of rain that looks like this to this more concentrated distribution of rain, kind of like I showed in that other picture. So the models do this. We don't fully understand why. We have some physical ideas, but this has some important consequences for a much warmer world. And here I will do a wild experiment if it allows me to switch. Yeah, first I just wanted to say that this idea of the convection jumping together is shown here. So this is another calculation where this would be the world. This would be a horizontal distance. So this would be a doubly periodic. This would be sort of east-west and north-south. And here you can hardly see anything, but what the color is how frequently it rains at a given point. So here it rains, and the black it doesn't rain. And what you find is you see this coarsening of the rain. And what you find is that the non-raining areas, these black regions, so each one of these is a day. It's like a calendar. This is first day, second day, third day. And what you find is that as time goes by through the calendar, these dry regions get bigger and bigger and bigger and bigger. So eventually all of the rain is clustered into one spot, like we showed before. And because of this, what I showed before is what happens when you make the world really warm in these models, you get something really strange happening. So the first thing here is now I'm going to take this model and I'm going to run it for the present day conditions. And what you find is if you run it for many, many years, you find present day conditions in the tropics which look kind of like the present day. Everything's fine. You have temperatures around 300 Kelvin for the tropics. They vary from year to year. This looks like a perfectly reasonable model. If you change the amount of CO2, it's the same thing I was talking about before. You get an increase, more CO2. This is the amount of CO2 you can think about it. This is the temperature. As you increase CO2, the temperature of the model increases. It's just fine. But the big surprise is that if you increase the amount of CO2 a lot, something really strange happens to the planet. And what happens is that it just doesn't get warmer, but you get a planet where you have very warm temperatures with huge temperature swings. So now when we've increased the CO2 4 doublings, so it's a huge amount, it's like we might have had 60 million years ago, but a huge amount, what we find is that the planet gets these huge temperature swings, which has to do with this convection bunching together. The other thing is that instead of having very nice behavior in the planet, which is sort of right here, you get this wild behavior at very low temperatures and very high temperatures. So this again is how temperature changes versus how strongly you're increasing or decreasing the CO2. And the reason that happens is because as you get warmer and warmer in this strange planet, it's a uniform planet, is that the convection all bunches, this is again the planet, and what you see is the planet goes through these cycles where the whole globe is you get these huge areas where you just have giant regions of clouds which are reflecting light and giant regions of rain. So you get this giant clumping of convection which really affects the whole evolution of the global temperature. So I don't think that the world is of course going to do this, but what I wanted to say here was that the simple ideas that we have that help us understand the world in the sort of present conditions also lead to some very strange behavior in other climates, behavior that we don't understand very well, behavior that we don't know if it's very realistic, but it also makes it really fun to look at the climate problem. So here I'll just conclude by saying most of our understanding of the climate system is rooted in simple ideas. Clouds are uncertain. I didn't talk about that very much, but you can ask me later. These simple ideas lead us to expect maybe 2.5 degrees of warming for a doubling of CO2. They also help us understand why wet areas get wetter and dry areas get drier. But as we push the climate system to ever greater warming, what we see is that strange things start to happen, which we don't completely understand, or completely would be even an exaggeration, which we don't understand very well. And it motivates, I think, the basic science part of climate change research, because as the world gets warmer and warmer, we can expect things will happen that we didn't expect. You know, things, we'll be surprised. And we don't know what those surprises are, and this is a fun time to be in climate science because you can be at the frontier of trying to say, what are the surprises going to be? Maybe the surprises are a disaster, maybe they're great, but they're fun scientifically because the world will be very different. So sorry for the trouble with the projection, and thanks for your attention.
We have a few minutes for your questions. Yes?
Well, thank you. I have a question about the distribution of P minus E.
Yeah.
because I understood that the implicit hypothesis for that widening of the PDF is that the circulation stays the same.
Yeah.
And somehow your last conclusion there is also based on that hypothesis.
Exactly. I mean, that was the contrast, right? Because what we were doing in the beginning is we were saying our understanding of climate change is rooted in the idea that the circulation fairly stays about the same. But what we do notice is that this breaks down in our models. So at the beginning I was saying, here's our hypothesis. If you run the models in a narrow range, that works out fairly well. But as you push the models fairly hard, then you begin to see that this breaks down. And when that breaks down, you can have wild changes in the system. So that you're absolutely right. So if we're in this sort of range of small changes, then things are fine.
Yeah, but at the end, the PDF will try to come back to the equilibrium, right? I mean, I'm thinking about the Cenozoic and these periods, warmer periods, where you don't really have those really sharp difference between dry and wet zones. So I'm trying of imagining that during the transient response of the Earth to a warmer climate, things like that can happen. But then at the end, the equilibrium is restored, and then the PDF will.
Well, I think the equilibrium is only the fact that the area under the PDF, I mean, is that there's as much on the right side of zero as on the left side of zero. So when you integrate P minus E, it has to be zero over the whole PDF. So the PDF in equilibrium can be broader and still be in equilibrium. It's just that spatially or temporally, so you can have wet periods and dry periods, so you can think of this as happening spatially or temporally, that this will broaden.
Yeah, but what I tried to say is that would you expect in a warmer climate the PDF to be the difference between dry and wetter zones to be wider?
Yeah. So you would expect it to, if the circulation is constant, you would expect the PDF to be broadened. So at some point the circulation stops being constant, which in this sort of made up example I had at the end of a very simple planet, you can see how that changes. But as long as the circulation doesn't change a lot, the difference in the last planet I showed, that very simple planet, was there was no large-scale thing that affected the circulation. Right now, when our planet, it rotates, it gets different amount of heat at the pole and at the equator. So this controls the circulation to some degree. In that planet that I showed that where you got this very wild change, I stopped the rotation, I made the radiation be the same everywhere, and this allowed the circulation to be much more sensitive to how things were behaving. So it was a bit of an artificial example, but it was just showing you a little bit about how you can get some surprising behavior. Yeah.
Thank you for the talk. So continuing with the comment of Jorge behind, therefore, one would expect in the sea surface, in the surface of the ocean, that trends in surface salinity would be more intense because of the P minus E contrast. That would be the consistent thing with increasing the contrasts of dry and very intense precipitation records, because you enhance evaporations in some regions and precipitation in others. Therefore, over the regions where you enhance precipitation, salinity changes in contrast to the other regions. Yeah. And this is something which has been measured in the last few decades in consistency with that.
Okay. Yeah. So just to repeat that, the point was that you would expect this, if you have more evaporation, then you take fresh water away from the ocean, so you increase the salinity, and then if you have more precipitation in the wet regions, you have more fresh water raining, so you decrease the salinity. So you'd expect the signature of this to be represented in the salinity signal of the ocean, and indeed
you see that in the observations, so which is a good support of this basic ideas. Physical principle. Yeah. Can I have another question? Yeah, I'd like to hear maybe your opinion on the present population of climate models and their equilibrium climate sensitivities.
Yeah.
How much role the different representation of clouds has on this variety of model responses. And so, if you would like to say some words about model tuning and the tuning of clouds in the models, and how this affect both climate sensitivity and how much space there is for doing this in a reasonable way?
So when we construct climate models, let's see if I can, maybe I will do it without the slides because some of them are quite big, but so we make these climate models, and we like to say they're very sophisticated and they obey the laws of nature and all of that, but it's only partly true. So the models are based on fluid dynamical principles which work well in the mid-latitudes. They're quasi-two-dimensional. But the whole vertical energy transport in the models is made up by sort of statistical empirical rules of thumb. So we call that convective parameterization or parameterization of clouds. But the way the energy transport in the vertical is sort of made up by people trying to be sensible, but they're not rooted as strongly in basic laws of physics. And because of that, there's some freedom in how you play with these parameterizations. And so normally when you put a model together, you have the fluid dynamics and the radiative transfer, which are on good physical grounds, but your model might make too many clouds here or too few clouds there. So people then will adjust the parameters of these small, of these schemes to try to get a reasonable looking climate. And this is what they call model tuning. Often model tuning is really a way to compensate errors because we know we have parts of the model which are wrong, and then we have other parts of the model which are wrong, and we can play with the parameters to try to get a reasonable climate. So because of this, the models aren't really that suitable for telling you how the clouds will change in the future, I don't think. I think they're good for testing this assumption of whether the circulation controls the humidity, which is what I was saying, because you have the large-scale circulation which transports the water vapor. But I don't think the models are that adequate for controlling clouds, and that's why over the last 40 years, if you look at very primitive versions of the model to very elaborate versions of the model, we haven't narrowed our estimate of how sensitive the planet is, or we haven't reduced the uncertainty associated with clouds. But the exciting thing is, and I don't have a hope, I think, of showing that, but if somebody wants to look at a video later, is that we now have a new class of models that we're developing which actually can replace some of these statistical laws of thumb with more basic principles. And we're just now in the position where we have enough computer power to run these models. So I hope that this will help us. And there's other reasons using observations and data where we might be able to constrain the clouds. So that's a huge topic, but the models aren't that trustworthy for clouds. There's other reasons to believe what the climate sensitivity is that's not related to the models. But most of the things that we believe and understand isn't because a model says it, it's because we can fit it in our head and understand it.
Any other questions?
I would like to make a general comment on your presentation. From what I gather, you have, I think, convinced us that the evolution of clouds and correspondingly the precipitation of water and so on is extremely sensitive to the humidity. On the other hand, I understand that the concentration of CO2 is also very important, to the point that one molecule of CO2 in 10,000 or something like that makes already a change. So this extreme sensitivity points out to the fact, to the well-known fact, in fact, that weather has chaotic behavior. On the other hand, you have made a definite prediction, which is that evolution is going to be towards having changes which are in the extremes, which is not a chaotic prediction at all. It means that something clearly definite is coming out. Is there a contradiction between these two visions?
Well, if I understood the question right, I would say no, because the chaotic behavior of the system we normally think of, imagine a dynamical system where you're just following the evolution of the state of the system on a trajectory. So it's moving through the phase space or the state space of your world. So what's chaotic is the path. But what we think is predictable is the attractor or the basin in which that trajectory moves.
I see.
So that's the premise of the climate science, is that the attractor is the climate. So the attractor is, this trajectory is moving around on some manifold in space.
So the attractor is clear, but what does the attractor is what makes the situation definite.
This is how we think about it. You know, we only have one climate, we only have one history. we can't be too overconfident, but the general thinking is that, and from what we see from all the models that we can construct and what we see from the past Earth's history, is that the attractor on which its trajectory moves is predictable.
It is like
planetary motion.
Planetary motion is also chaotic, but it is the differences are concentrated in very small margins, so that in practical terms it is not noticed. The other thing that I wanted to comment is on practical terms. This is never mentioned when the people speak about climatic change, which is clearly something which has a great anthropogenic contribution now. But is there any hope for the future? Because hope, yes, because as I like to say, in my lifetime, which already is quite a bit long, the human population has multiplied by 3. So it has gone from 2,500 to about 7,500 people. So if these people have or reach a level of life which I will not say is similar to the United States, but some normal regions in Europe, this is going to increase the percent of CO2 in the atmosphere enormously.
So
the population is going to grow still. I think that it will reach 9,000 million or 10,000 before it gets down, if there is not a cataclysmatic even before. So I cannot imagine how this is going to be tempered. And nobody mentions this. I remember, because I am old enough, as I said, the effect, the enormous effect, the impact that was produced when the Round Club issued this report, The Limits of Growth. But this is never mentioned again.
You know where I'm a little bit optimistic. So the question was,
is there any hope? I'm not certain.
Yeah, I will try to give you some hope. So the hope is, so the question is, we have populations exploding, and if people try to have the same sort of wealth as the more developed countries, that implies huge amounts of CO2, huge amount of energy, huge amount of resource usage. But if you do look at human history, we're pretty good at solving problems. So I live in North Germany, and 20 years ago in North Germany, you couldn't swim in hardly any river, you couldn't swim in hardly any lake. Most of the forests, people were worried about dying. And if you look at 30 years ago, most people worried about people dying of starvation. So if you look at the Club of Rome in the 70s, they talked about the looming, crisis of nourishment. Today, more people die of overeating than from undereating in the world. I mean, overeating is a bigger, from what I read, a bigger, so that doesn't mean that, to me that's optimistic, because if we're dying from overeating, that's also a solvable problem. But we've solved so many local problems in terms of air pollution, in terms of water. So if we want to, as a species, we're pretty good at solving problems. We're better solving acute problems, ones which are really confronting us today. Climate change is a hard one because it's a problem that comes over a long period of time. So this is a harder problem for us to solve. But we're pretty good at solving problems. We're pretty good at changing our environment. So that's what these guys in the back row here are for, who are under 30. So I'd like to be optimistic, but I'll be dead eventually and it won't matter. So yeah.
Maybe one last question? No? Okay, so thank you very much, everybody. Thank you very much for this talk.